So let's get out our claim here. And remember how we're going to prove this. We're going to try to prove this by proving the base case and then proving the inductive step. That P of n implies P of n plus 1 for all n bigger than or equal to the base case. The proof goes like this. Proof. It would say proof by weak mathematical induction on n. So here we have the base case. In the base case, what we're trying to do is we want to show that P of 13 is true. And this is where we make in factorial greater than 5n, we make this equal to P of n. So if that's like your predicate, you're saying P of n is true if n factorial is greater than 5n. We want to show P of 13 is true, i.e. 13 factorial is greater than 5n. So let's just do it. So we're going to say let n equal to 13. Then note that n factorial equals 13 factorial, which if I get out my calculator, or let's see if Siri's got this. Siri, what's 13 factorial?
13 factorial is 6,227,020,800.
Look at that. Thank you very much, Siri. So according to Siri, 13 factorial is 6,227,020,800. So that's 13 factorial. The number of ways you can pick 13 things out of a hat, you'd almost get all of Jeff Bezos. You get like a small percentage of Jeff Bezos' net worth. So that's n factorial. Further, the question is 5 to the n, which equals 5 to the 13. What's that, Siri? Siri, what's 5 raised to the 13th power?
5 raised to the 13th power is 1,220,700,8,125.
So according to Siri, that's 1,220,703,125. The point being, just checking 5 to the 13 and 13 factorial, we see 13 factorial is in fact bigger than 5 to the 13. Thus, n factorial, which equals 13 factorial, is in fact bigger than 5 to the 13, which equals 5 to the n. Hence, the base case holds. So the base case is much more computational. It's just we have to show this one thing is true, just do it. All right. Any questions on that? Good. So that brings us to the inductive step. And here, remember, we want to show that that for all n greater than or equal to 13, as to connect to the base case, P of n is greater, or sorry, P of n implies P of n plus 1. So in our particular example, we want to show that for all n greater than or equal to 13, n factorial greater than or equal to 5 to the n, n factorial greater than or equal to 5 to the n, or maybe I'll say if n factorial greater than or equal to 5 to the n, then n plus 1 factorial is greater than or equal to 5 to the n plus 1. So that's what we're trying to show. And I just remembered that I meant to give you guys a lemma to do this, to help do this. We can do it without it, but it'll help. And the lemma says, for all real numbers, or I'll say for all positive real numbers, A is greater than B and X greater than Y, AX is greater than BY. Which I think makes a lot of sense, right? We're saying if A is bigger than B and X is bigger than Y, then certainly A times X, right? The product of the two bigger things is bigger than B times Y, the product of the two smaller things. But we haven't proven it yet. So theoretically, if I didn't tell you this, you need to prove it. But I'm telling you this is a fact, so you don't need to prove it. Maybe I'll prove it later if we have time. Probably not. So anyway, let's just get started. So we want to show this, right? This is a for all statement. So we have a mini proof here inside of our inductive step, which is a for all statement. The way to prove a for all statement, you could use method of exhaustion. We can't do that because we have an infinite set here. So instead, let's use a direct proof. So let's go ahead and say, let n be any arbitrary / particular integer such that n is greater than or equal to 13. So we have the domain, right? And now we want to assume the hypothesis. We want to assume the hypothesis and show the conclusion. We want to say that in the assumption that n factorial is greater than 5n, we can show n plus 1 factorial is greater than 5n plus 1. So assume n factorial is greater than 5n. All right. Now, how do you guys think we can get from this fact to proving this?
You can turn n plus 1 factorial to n factorial times n plus 1.
You're saying n plus 1 factorial is n plus 1, perfect, yeah, times n factorial, exactly.
And then you could turn 5 to the n plus 1 to 5 times 5 to the n. And then you can use the lemma. I don't know how you would prove that n plus 1 is bigger than 5, though.
I'm glad that
Oh, wait. It's bigger than 13.
It's bigger than 13.
Yeah,
so it's clearly bigger than 5.
Yeah,
Tor, this is a fantastic idea. Tor recognizes that, hey, we can get from n to n plus 1 factorial just by multiplying n factorial by n plus 1. Because that's what it kind of means, right? N factorial is the multiple of everything from 1 to n. But if you multiply an n plus 1 on top of that, well, this whole product is the multiplication of everything from 1 to n plus 1, which is n plus 1 factorial. And then he also recognizes that 5 to the n is 5 multiplied by itself n times. We multiply another 5 on top of that, that's 5 multiplied by itself n plus 1 times. So if you know n factorial is bigger than 5n, which you're saying it is by assumption, and n plus 1 is greater than 5, which it must be because n is greater than or equal to 13, meaning n plus 1 in particular is bigger than or equal to 13, which is bigger than 5. Well, by our lemma, right, if you multiply the two bigger things, it'll be bigger than if you multiply the two smaller things. So n plus 1 times n factorial should be bigger than 5 times 5 to the n. But like we just argued, this is just n plus 1 factorial on this side, and this is just 5 to the n plus 1 on this side. Very good, Toro. Very, very good. And this time I'm not giving Liam credit. That's what you did. That's all you, Toro.
That it was all me.
So that's the idea. So let's note a couple things. Let's say note, since n is greater than or equal to 13, n plus 1 is greater than or equal to 13 plus 1, which equals 14, by adding 1 to both sides. Normally we'd do this in kind of like the center. We'd say like, oh, n plus 1 is greater than 13 plus 1. But since it's just one line, you can do it like this. Yeah, so further, n plus 1 greater than or equal to 14 is greater than 5. Thus, by transitivity, n plus 1 is greater than 5. That just says that because n plus 1 is bigger than or equal to 14, 14 is bigger than 5, n plus 1 is bigger than 5. Which makes sense, right? Hence, by our lemma, because n factorial is greater than 5 to the n, and n plus 1 is greater than 5, then n plus 1 times n factorial is greater than 5 times 5 factorial. So that's the big idea right there using the lemma. Then we can use Torio's great observation to show, note that n plus 1 times n factorial greater than 5 times 5 factorial by given by above. That implies that n factorial is greater than 5 times 5 factorial, or sorry, n plus 1 factorial, by definition of factorial. And that implies n plus 1 factorial. All right, this would be, sorry, oh my gosh. This is 5 times 5 to the n. What am I doing? I'm just trying to transcribe that line there and I messed it up twice. So the n plus 1 times n factorial greater than 5 times 5 to the n, meaning n plus 1 factorial, we said that that's what this equals, greater than 5 times 5 to the n. And then 5 times 5 to the n, we said is 5 to the n plus 1. By definition of exponentiation. Thus, assuming n factorial is greater than or equal to 5 to the n, we have shown n plus 1 factorial is greater than 5 to the n plus 1. So what this means is that if at any point, if at any n factorial gets bigger than 5 to the n, well, it's guaranteed n plus 1 factorial is bigger than 5 to the n plus 1. Meaning it's guaranteed that 5 to the n plus 2 factorial is bigger than 5 to the n plus 2. It's guaranteed that like n plus 2 factorial is greater than 5 to the n plus 2. N plus 3 factorial is greater than 5 to the n plus 3. Then you have that chain reaction. It just keeps going forever. Once you show it happens once, it'll happen for all n bigger than or equal to that. And that's where the base case comes in because we showed it once. We showed it works for 13, so it must work for everything bigger than or equal to 13. And so here's the part, I'll just put the conclusion down here in blue. This is normally where you have conclusion. N factorial greater than 5 to the n for all integer n greater than or equal to 13. Any questions?
Why 13?
That's a good question. Because I have actually a table that I have on my graphing calculator app here. Well, in the beginning, clearly 5 to the end is going to be bigger than n factorial because, like, for example, if you look at 3 factorial, that's 3 times 2 times 1, where 5 to the 3 is 5 times 5. So, so every factor there in 3 factorial, 1, 2, and 3 is less than 5. And so clearly 3 factorial is going to be less than 5 to the 3. Same thing with 4 factorial. That's 1 times 2 times 3 times 4. And 5 to the 4 is 5 times 5 times 5 times 5. Again, every factor in the 5 case is bigger. Once you get to 5 factorial, you get to the first one where it's kind of like you have one factor that's equal. You have 1 times 2 times 3 times 4 times 5. Whereas 5 factorial, you have 5 times 5 times 5 times 5 times 5. So almost all the factors are bigger, but not quite. The point is, if you play that logic out, it turns out you have to get to 13, I think. Actually, let's see if 12 actually works. No, 12 doesn't work. So you have to get to 13 to find the first one where finally in factorial can eke past 5 to the end. And you think it should eventually, because once you get past a certain point, like 5 is just multiplying 5 times 5 times 5 times 5 times 5. Once you get 13 factorial, you do 1 times 3 times 4 times 5, smaller than 5, but then times 6, times 7, times 8, times 9, times 10, times 11, times 7, times 13, right? All bigger than 5. So there's like a balance there that eventually gets overcome between 12 and 13. Make sense, kind of?